We're going to be spending a few days, a couple of weeks, probably 3 or 4 weeks, talking about forces. Henry, forces are used in engineering. They're used in explaining how things move. And really, if you asked me to pick sort of the dawn or the birth of modern physics, well, I guess modern physics is with Einstein, of classical physics, it started here with Isaac Newton. So we're going to start out with what are Newton's laws of motion. First of all, we need to define a force. A force is a push or a pull. Tato, that's already wrong. The modern definition of a force is that it's an interaction between two objects. That's too vague for me. And a lot of the time, what I'm going to be teaching you is technically wrong. In physics, we say there's only 4 fundamental forces, and I'll talk about those. But we're not going to go down that rabbit hole of detail, because everything, when it comes right down to it, is subatomic particles exchanging energies. We're not going to go that far down every time. We're going to stay at the higher level. Okay? Is force a vector or a scalar? Does the direction that you push make a difference? Yeah. Absolutely. Prove it. Okay. Gio, could you stand up, please? Kiana, could you stand up, please? So Kiana, did the direction that we pushed make a difference? So does force have direction? It's a vector. Symbol for force, capital F. The units, we measure force in newtons. Symbol capital N. Bit of a problem with the letter N because it's also a direction north. It's also sometimes used as an abbreviation for something else. We don't have enough letters in the English alphabet, so when it appears after a number, it's a unit. By the way, force is measured in pounds in the imperial system. So, okay. We're often going to be talking about the net force. Forces can be added, forces can be combined, as Kiana experienced, but the direction matters. Example 1 says, find the net force in the following diagrams, and just for giggles, let's add a compass rose right here, so that if it ends up going to the right, we'll call that east. If it ends up going down the page, we'll call that south. If it ends up going up the page, we'll call that north. If it ends up going to the left, we'll call that west. If we're pushing with 5 newtons that way and 2 newtons that way, what would the net force be? 7 newtons direction? Okay. We typically, to show it's a direction, put an @ symbol, and that way you know the east is actually east and not E for electric field, which is also what it's an abbreviation for. 7 newtons, @ symbol, east. I have the same 2 forces, or do I? B, what do you think my net force is here? Yes, what was that? 3 newtons, east. 5 to the right, 2 to the left, that's the same as net 3 to the left. By the way, on you, when you weren't moving, we had Gio and I pushing, they were exactly canceling out. You know what the force was on you when we were pushing in opposite directions? The net force was 0. That's why I set it up that way. Oh, C. What's the net force here? 0. D. In Physics 12, we'll revisit all of this stuff, as Ryland knows, but we'll say, okay, what if we let you push at a slant, at an angle? What if we have 2 dimensions? But I'm not going to answer that right now. Newton's laws of motion. I got to go on my Isaac Newton rant, so put your pencils down. So Newton's laws of motion. Newton came along and he said, I'm sorry, 2,000 years of what you call science is incorrect. I can explain how this works, and I can explain it succinctly. 3 rules, Newton's 3 laws. The first law, it's often called the law of inertia. Here's what it said. Typically it's phrased, objects at rest tend to remain at rest, objects in motion tend to remain in motion, which is a terrible phrasing. Here's what it says, and you're going to underline some words with me. In the absence of an unbalanced net force, in other words, if the force is 0, if there is no unbalanced force, if the total force acting on you is 0, Kiana, that doesn't mean there's no forces acting on you. It could be like situation number C, letter C, where there are 2 forces acting, but the net force is 0. So if you know the net force is 0, you know what? Let's write a little f with a subscript net, N-E-T. The overall force is 0. An object will either remain at rest or move in a straight line at a constant speed. If F net equals 0, then A equals 0. That's the shortest way to write it. If there's no unbalanced force on you, you can't accelerate. Which means if you're already at rest, you're going to stay at rest. Or if you're moving in a straight line at 6 meters per second, you're going to keep going in a straight line at 6 meters per second. You're not going to slow down or speed up. So let me read that again. In the absence of an unbalanced net force, an object will either remain at rest or move in a straight line at a constant speed. You know what? If there is no unbalanced force acting on you, Geo, your acceleration will be 0. You can reverse it. If you notice that an object is accelerating, which means it can be changing its speed or direction, then there must be an unbalanced force acting on the object. Oh, if you're speeding up or slowing down, there has to be an unbalanced force. I'd like you to imagine you're a passenger in the car, and the car makes a sudden left turn. What do you feel? Well, from your own experience, you might think that you're getting pushed to the right. You're not. And this is, I told you already, that your body is a backwards accelerometer, and now we're going to start to explain why that is the case. I did tell you that when you hit the brakes, you feel like you're getting pushed forward, you're accelerating backwards. When you floor it, you feel like you're getting pushed backwards, your body is accelerating forwards. We talked about the elevator. What's really going on is Newton's first law kicks in. Your body wants to keep going in a straight line at a steady speed. The only way that we can change your direction is to apply an unbalanced force on you. The door pushes against you. Now you think it's because you're getting pushed against the door. No. It's the door had to push against you, otherwise you would have kept going in a straight line at a steady speed. So contrary to what your common sense might tell you, you're not being pushed to the right at all. The driver steers the car to the left. Your body, Newton's first law kicks in, wants to keep going in a straight line at a steady speed, but the door is moving left with the rest of the car. Your body runs into the door applies a force against you to turn you around the corner to change your direction. Your grandfather, before you turn the page, talk to your grandfather. Your granddad might know this trick. See if he'll fess up. In the 1950s and in the 1960s, back then seatbelt laws weren't mandatory, so people didn't wear seatbelts. And back then, cars had bench seats, not bucket seats. And so if you were a young teenager and you were going out on a date with a girl, back then the guy was going to be the driver, you would get some surfboard wax and you would wax down the passenger seat so it was slippery. And then you would drive with your arm sitting like this on the bench seat, and you would make a quick right turn, and the girl would come scooching across towards you. And, oh, hi, honey, that's very nice. Ask your grandfather, he might fess up. Really, by the way, what was happening was the girl was going in a straight line at a steady speed. The car was turning underneath her. She wasn't scooching across. In fact, the driver was moving towards her. As a general rule, now you can turn the page. Any object tends to continue moving with whatever speed and direction it presently has. Oh, and this can include zero speed, of course, at rest. When your driver accelerates the car, your body wants to stay where it is. That's Newton's first law. In order for you to accelerate forwards, the seat that you're sitting in has to apply a force against you to accelerate you forwards, and to you it feels like you got pushed backwards, but that's because your body wants to stay where it is. It's the seat accelerating you forwards. That's why your body is a backwards accelerometer. This tendency that all massive bodies have to resist change in their states of motion is given a special name. We call this inertia. Every object in the universe that has mass has this property called inertia. You can kind of think of inertia as the laziness of an object or its resistance to change. The more inertia an object has, the larger a force you have to apply to get it to change its motion state. Okay? Who has more inertia, Geo or Tato? Geo. Why? Talk about that. Well, what has more inertia, a bicycle or a logging truck? Because it has so much more inertia, that means the logging truck is more difficult to get moving. If you've ever been at a red light behind a logging truck, you'll notice it takes them a long time to get moving. More difficult to stop. If you're driving a logging truck, you learn that you have to start hitting your brakes far sooner than when you're in a car. And more difficult to go around a corner, because to change its direction, it has a lot of inertia. It wants to keep going in a straight line. It's why logging trucks are more likely to tip over than a little Austin Mini. How do we measure inertia? Mass. That's technically not true. Technically, mass and inertia are the same when we're not going at relativistic speeds. I fibbed to you a little bit last unit. I taught you that as objects speed up, their mass increases. What's really changing is their inertia is increasing. The amount of energy required and force required to get them to move is what's increasing. I didn't say that last unit. So, inertia or mass resists a force. In fact, you can think of mass as a measure of the laziness of an object. The more mass an object has, the less willing it is to change its motion state. You have more mass than Tato. For us to get you to move, this is an advantage you found in football and in basketball. People can't move you around very easy, can they? No. Okay? Probably people move Alec around a lot easier than you. Yes? Yeah. Now, there's tricks that you can do, and I'll teach you some of them later on this unit, to try and improve your ability to exert a force against a larger object. The problem is, if that larger object also knows the tricks, you're in trouble. Car accident story. In 1996-97, I was doing my student teaching, and on the freeway, I got rear-ended by a semi-truck just before the Burnett overpass, off-ramp. So it was stop-and-go traffic. It was during rush hour, and the person in front of me hit their brakes really quick, so I had to hit my brakes really quick, and the truck driver had just looked down to grab his coffee mug, and by the time he looked up, he'd hit me. This tells you how long ago it was. I was driving a 1980 little Honda sedan, and it had an ashtray. Cars hardly have ashtrays anymore. And in that ashtray, I kept all of my change, all of my toonies and loonies and quarters and dimes. And so there was some mass in there. When I got rear-ended, the ashtray shot over my shoulder and hit the back seat. No, it didn't. That's what it appeared to me. The ashtray had enough inertia, resistance to force. It stayed where it was in one place. My car got thrown forward by the semi-truck, and because I was attached to my car, it appeared to me as though my ashtray went whipping over my shoulder. That is not what happened. Actually, it stayed where it was, and I went shooting forward. Put your pencils down. So Newton's first law explains what it takes to get an object to accelerate. An unbalanced force. If your net force is 0, you're not accelerating. Oh, and it also says the thing that resists acceleration is called inertia, mass. So the short version of Newton's first law, if an object is accelerating, there must be an unbalanced blank acting on the object. What word goes in the blank? Force. And it works backwards. If an object is accelerating, if if there is an unbalanced force acting on an object, the object must be accelerating. And remember, this is important. There's two ways to accelerate. You can change your speed, or you can change your direction. When you're going around a car corner with your car, even though your speed's not changing, you are accelerating because your direction is changing. Proof that direction matters for forces. Chris Angel's superhuman strength trick. I already did that one. Elliot, did you see how I did it? I locked my hands underneath your elbows and I applied an unbalanced force up. Because of that, you had to accelerate up, and I channeled all of their forces up along with you. I've done that before and actually lifted kids right off the ground doing it. Look how Chris Angel did his trick. Hey, how does Newton's first law help explain how seatbelts save lives? If the seatbelt wasn't there, what would your body want to do? Keep going in a straight line at a steady speed. Okay? So, prevents body from going in straight line at steady speed. Very simple, very basic device, but until seatbelts were made mandatory, well, what do you yell when you want the front seat? This is why the front seat is called the shotgun seat. I don't know if you've ever wondered where the expression comes from. It's from before seat belts. The front passenger seat was called the shotgun seat, and the joke you would make was, if we're in an accident, I'll be the first one out to inspect the damage because I'll be going through the windshield and I'll check it on the way by. Okay? Did you never wonder why you call it shotgun? What a stupid expression. No, you were in the shotgun seat. You're going to be launched. Why don't they call the drivers the shotgun seat? What prevents the driver from going through the windshield? The driver's going to hit the steering wheel and die that way, but he's not going through the windshield. Okay? The moral of the story, Sarah, wear your seatbelts. They become comfortable, wear them. Turn the page. Newton's first law is very powerful because it helps you reason your way to any missing forces. So Manuel weighs 1,000 newtons, that picture right there, and stands in the middle of a board that weighs 200 newtons. The ends of the board rest on bathroom scales, and we're going to assume the weight of the board acts at its center. Fill in the correct weight reading on each scale. What's the total force down? Add it in your head. 1,200. Is Manuel sinking into the ground like quicksand? Say no. Is he flying into you like Superman? Say no. That means the forces must be, I'm looking for a word that begins with the letter B, balanced. How much must each scale be pushing up at? No, that'd be 2,400. Sorry, how much? 600 apiece. My forces are now balanced. How do I know they're balanced? Because I'm not sinking into the ground like quicksand, and I'm not flying into the air like Superman. I'm not accelerating. Situation number 2, Manuel's going to move sideways, so he's standing closer to one of the scales. Now, the scale that he's closest to reads 850 newtons up. What must this scale read exactly? 350. So that forces are still balanced. How do I know they're balanced? Because he's not sinking into the ground like quicksand, and he's not flying into the air like Superman. Yes, Rylan, it starts now. Yes, look. It's just around the corner. We'll get there. All my dumb expressions. Third one here. Now we're going to be measuring force in tons. That's part of the imperial system, pounds and tons. But a 12-ton truck is 1/4 of the way across a bridge. The bridge weighs 20 tons. On the right-hand side, there's a 13-ton of force pushing up. What must be pushing up on the left-hand side? Well, is the bridge and truck sinking into the ground like quicksand? Is it flying into the air like Superman? Then the forces must be, I'm looking for a word that begins with the letter B, balanced. So, sorry? 19. I got 32 down. I have to have 32 tons up. Okay. That's Newton's first, the law of inertia. If you're accelerating, forces are unbalanced. If forces aren't unbalanced, if forces are balanced, you can't be accelerating. Newton's second law is the equation. It tells us to calculate how big the force is. Force equals mass times acceleration. It's a vector, so I'm going to put a vector arrow above the F and a vector arrow above the A, although we'll often be sloppy and just include the directions in pictures and things without being this fussy. Where the M stands for the mass in kilograms and the A is acceleration in meters per second squared. It's sometimes written this way. How would you get the A by itself? If you're interested in getting an object to accelerate, you either need to push harder or make it lighter. There's rocket science in a nutshell. You need a bigger engine or a lighter rocket if you want to get off of Earth. Okay? It's more complicated than that, but yeah. Yeah? Go ahead, Henry, if you need to go ahead. You can't? Okay, could you get him a tissue, Rick? Or two? There's Kleenexes there? Little note. This also means that 1 Newton equals 1 kilogram meter per second squared. If, after all, if force is mass times acceleration, mass is kilograms, acceleration is meters per second squared, then a Newton is a kilogram meters per second squared. And in fact, that's how acceleration was calculated, but about 150, 200 years ago, we renamed this unit, we called it a Newton. Malcolm has a mass of 65 kilograms. What's the magnitude of the gravitational force acting upon him? What does this want me to find? Force. F equals ma. Which A? So 65 times 9.8. I chucked the negative because I just asked for the magnitude. What's the gravitational force pulling down on someone who has a mass of 65 kilograms? I should be able to do this in my head. It's going to be 650 take away 13. It's going to be 637? Yes? Units for force, newtons. Here's your new unit for this unit. By the way, the force of gravity has a special name. We call it weight. Your weight is not measured in kilograms. Your weight is measured in newtons. In English, people are sloppy that way. They'll say, oh, I have a weight of 28 kilograms, 55 kilograms, 62 kilograms. That's the mass. The weight should be measured in newtons. All right, let's do some rocket science. I told you this was the beginning of rocket science. The space shuttle has a mass of 2.03 times 10 to the 6th, which it does. If each engine is capable of exerting a force of 12.5, capital M is mega, yes, newtons, and that is accurate. I Googled this. Okay, what's the maximum acceleration of the space shuttle? There are 2 engines. What's this question asking me to find? Hey, let's go back to our DFIC approach. Let's write A equals question mark. Now, normally when we wrote A equals question mark, we'd be looking for VF and VI and T and D. No. Now we have another way to calculate acceleration using force and mass. Which one do I use? I read the question. What's that 2.03 times 10 to the 6th? How do you know? This is why it's worth memorizing what units go with what. Kilograms is mass. So I can say M equals 2.03 times 10 to the 6th. Now I say, aha, I'm thinking forces, not VF and VI and AT. I've got an M in the equation. Please, did they also by chance give me a mass? A force? 12.5 what? What's mega the same as? 10 to the what from your sheet? 10 to the what? Sixth. This is wrong. Why is this wrong? What? Okay, in front, I'm going to go 2 times that. 2 engines. Why do we have 2? Because there's 2 engines. I'm sorry, I'm not going to change it. These are the 2 big side engines that you used to see on the space shuttle. The solid fuel booster rockets. Okay. Do I have an equation with an F and an M and an A in it? I do. Let's write it down since this is the first time we've officially written this equation down. Connor, what do we want to get by itself? How would I get the A by itself? More specific, divide by what? The M or the A? The M, yeah. Because some people say divide by the A. No, I want the A to stay there, right? All right. The force is going to be 2 times 12.5 times 10 to the 6th. The mass is 2.03 times 10 to the 6th. Psst, psst, psst. Is there a 10 to the 6th on the top? Is there a 10 to the 6th on the bottom? Is everything being multiplied? Then what can I say about those? That's convenient. So it's going to be 2 times 12.5 divided by 2.03, which is what? 12. I should really go to 3 sig figs technically here because of the 2.03 and the 12.5. How many G's is that? Divide by 9.8. How many G's is that? Wait a minute, Mr. Duick. I heard that astronauts experience like 3 G's or 4 G's or 6 G's. 1 point, huh? Are they lying? B. Why does the maximum acceleration change as the engines burn? Because it does. Why does the acceleration change as the engines burn? Nope. By the way, up at the ISS, if you calculate G, it's about 9.7. Not 9.8, but it's 9.7. They're not out of the gravitational pull of the Earth. How are they floating up there? We'll talk about that later. But for now, Zach. Why do they have more acceleration? Nope. Speeding up just means you're speeding up. That's what acceleration does. Why is acceleration itself increasing? Elliot. And if your fuel burns in this equation here, what number is getting smaller? Mass. Because you're burning fuel. And as that number gets smaller, but the force stays the same because the engines are still at full output, if you divide by a smaller number, what happens to your new answer? My abbreviation for gets bigger and smaller, I usually do an up arrow for increases. And to be honest, normally I do a down arrow for decreases. I wrote get smaller, but I'm not going to do that again. I'll do down arrow and up arrow, increases and decreases. You've clued in, I tend to abbreviate, right? How does Newton's second law help explain why a sprinter might want to wear lightweight shoes? Okay, so let's suppose you're Usain Bolt. And you've lifted weights as much as you can. You've maximized the force. If this is maxed out, Tato, how can I get a bigger acceleration? As M increases, A increases. It's why the sprinters wear very lightweight clothing and low mass shoes. Which again, I mean, you've clued in, you don't want to run a sprinter's race in work boots, but here's the physics of why. Okay. Newton's third law. Turn the page. Probably the most misunderstood one. Newton's third says this: for every action there is an equal and opposite reaction. That's typically how it's phrased. And to you I say, huh? Here's Mr. Dueck's version. Forces come in pairs. Forces come in what? Pairs. Forces come in what? Pairs. Newton's third, forces come in pairs. Or if you want to write it algebraically, the force of object A on object B is the same as the force of object B on object A, except in the opposite direction. What would be a nice, easy way to show in the opposite direction? Yep. You cannot, Catherine, you cannot have a force all by itself. Forces come in pairs. You can't push on something without getting pushed back. Speaking of pushing, how does Newton's third law help to explain why it's difficult to walk or drive on ice? By the way, you guys, please don't tell me you think that it's your tires that make you go forwards in a car. Which way? Think about it. Which way do your tires push? They push backwards, right? So what force pushes a car forwards? It's the same one that pushes a human forwards when walking. Zach, you named it. No, you gave it a name. Friction. This is why it's so tough to drive on ice, because on ice, oh, on ice, almost no friction. So although forces come in pairs, the pair force is so small and the car has so much inertia, the car is going to end up going in a straight line at a steady speed. Well, we'll get one in right now. But let me pause.